All right, hello everyone, and welcome to my channel. Sorry, I'm a little bit preoccupied here, trying to get it together. Okay, this is an educational channel, and we try to take deep dives into some great theories of everything that you may not know about, that would help you with your paradigm shifting and your 5D consciousness, your holistic worldview. And today is our 453rd video that we've done on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson was an American engineer. In 1959, he proposed his two fundamental postulates, 7 assumptions about how he believed the universe operated, that he gleaned from extensive inductive work of poring over a lot of data and having a few epiphanies. And then he took those two postulates and through a process of deduction, he arrived at a theoretical universe about how he believed that the universe would look if his postulates were correct. And he published his results, in particular, comparing his results with the scientists, their observations, their empirical measurements that they compiled in their scientific tables. We're looking at a book here that is called Basic Properties of Matter. This is a book he did in 1987, just 3 years before he died. That has to do with chemistry primarily, and he derives equations for many of the basic properties of matter, such as the interatomic distance and the specific heat and the compressibility. And then he compares a lot of his findings with the tables. Now, I think we have a pretty long segment. We're going to try to finish this chapter. There is the chapter that we're looking at is called Specific Heat Patterns. And he does get off into the weeds here, into some very detailed stuff that you probably don't need to know at this stage of the investigation for you, or me, really. But I'm just trying to read this into the record so that if you are familiar with chemistry or organic chemistry and you want to get further into this, that you can. But Larson, the bulk of the content of his postulates is in the first postulate, which includes 4 assumptions. The universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. The second postulate has the other 3 assumptions, and this is primarily mathematical in geometry. It's more axiomatic, just kind of like, if math works and geometry works, you have to kind of accept that if you want to go further. And so the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. There are some issues with that second postulate that some of Larson's associates have raised, and I agree with them. Euclidean geometry, I think, is really just a subset of a larger set of geometries that are more inclusive and that would include more of Larson's universe. I don't believe that. So when Larson says that he is constructing his universe out of motion, he is really referring to something that is called scalar motion. And scalar motion is a motion that has a magnitude, but it has no specific direction. So you can envision a scalar motion as a, if you take a balloon and you put dots on the balloon, you blow up the balloon, all of the dots will be moving away from one another. And they won't be moving in any specific direction. Every dot will be moving away from every other dot. And even the locations between the dots, all of those locations will be moving away from each other. So there's no specific direction. It's really like every dot is moving in every direction. And I believe that right there pretty much goes beyond Euclidean geometry. And so one of Larson's revisers, Dr. Bruce Perret, who also recently passed away, proposed the idea of using projective geometry, which includes Euclidean geometry, as part of, as a subset of it. And I think the cascade goes from projective geometry to affine geometry to metric geometry, and then to Euclidean geometry. And so when you include all of those geometries, you have much better hope of encompassing the whole universe. Be that as it may, back to the scalar motion. So this universe is made out of scalar motion. That outward motion of the balloon, the dots on the balloon, is what Larson calls the progression. If you take the balloon and you suck it in, so the balloon is now contracting, all of the dots will be moving toward each other, but in no specific direction. That is what Larson calls gravitation. And that gravitational motion, or the progressive motion, if you arbitrarily decide that you're going to take one of those dots and assign it as a reference point, basically say that this particular dot is motionless, so I say, then you can start to suss out the directions of all the other dots are moving toward or away from that one dot. And it appears as if there's force fields between them, that there is a force of attraction between your dot and all the other dots, or repulsion. And that is not true. Each dot is pursuing its own course, but it appears an apparent force, or an as-if force. Now, it might seem kind of arcane to look at balloons with dots on it, but this is also was observed by Hubble back in the 1920s, that all of the distant galaxies are moving away from each other. So that is using that same model. That is a real physical thing, and if you believe in space and so on, that all of the distant galaxies are moving away from each other, which they use to justify the Big Bang. But the Big Bang would be more of a model where our galaxy would be at the center and everything would be exploding from our galaxy. Our galaxy would be still, and all these other galaxies would be moving away. But if we don't want to take that tack on it, then we would have to say that our galaxy is also participating in this expansion. So our galaxy is moving in every direction, as well as all these other galaxies. So that model actually does have a correspondence in reality. Okay, well, it is reality to start with, but in like physical phenomena. Okay, to go from there, motion, and motion is the relationship between space and time. That basically means a reciprocal relationship between space and time. And the car is moving 10 miles an hour. Speed, 10 miles of space in 1 hour of time. That's a fraction, space over time. And really, he applies that, and that's a reciprocal relationship. But Larson spreads that out and applies it to all physical phenomena are forms of motion, just like speed. They are all fractions with space or time as the numerator and time or space as the denominator, like matter, energy, force, acceleration, power, pressure. These are all fractions with space or time as the numerator and time or space as the denominator. But space or time can both be in multiple dimensions. As he says, space, time, and motion all come in 3 dimensions. And you can have more than that with these fractions because some of them are combined units. So you can get up to higher than 3 in your exponent. And this is a great way to identify units as well, because you get rid of the mass part of the MKS system. And so now you only have 2 variables, time and space. Now, time and space and matter, time and space and motion come in 3 dimensions. You have coordinate space, 3 dimensions of space. This is what we normally perceive in the universe. This is really where we establish a gravitational hold in the spatial reference system. 3 dimensions of space and clock time. The clock is still going in a scalar manner. So he calls that coordinate space and clock time. That's in the spatial reference system. And then we have the temporal reference system. It's inverse, 3 dimensions of time and 1 dimension and a scalar space. Space is always getting farther and farther apart. In the spatial reference system, its time is always getting later and later and later. But in no specific direction. And then, so we have this spatial reference system, the temporal reference system. But both of those, even though they require 3 dimensions of space and 3 dimensions of time, they only require 1 dimension of motion. So these other 2 dimensions of motion are basically beyond the reference system. Now, if you look at the discrete unit postulate, they come in only discrete units, space, time, and motion. You have to have a minimum unit of space before you have space. You have to have a minimum unit of time before you have time. These are small amounts, 2 millionths of an inch and 1.5 quadrillionths of a second. But well, it's actually 6.576 times 10 to the 15, so 6 quadrillion per second. And if you don't have that full unit, well, if you have 1 unit of space and 1 unit of time, space over time being speed, then you have this unit speed, what Larson calls unit speed. And that unit speed is also known as the speed of light. This is the speed of the progression. So Larson calls that the progression of the natural reference system. This is the natural reference system, the system to which nature actually conforms. Our spatial reference system and our temporal reference systems they're just abstractions. But the real reference system is a moving reference system, the progression of the natural reference system, moving outward at the speed of light in all directions. And so Larson takes his measurements from there, and that is the null point or the 0 point, meaning that half the universe is moving faster than that. Half is moving slower than the speed of light. The half that's moving slower is called the material sector. The half that's moving faster is called the cosmic sector. The material sector is for the spatial reference system. The cosmic sector is for the temporal reference system. And then also within each one of these sectors, you have a inside region that's inside a unit of space. That's called the time region, because if you don't have space, then you only have time, because it's got to be one or the other or both. And then in the cosmic sector, you have the space region, which is inside a unit of time. You don't have time, so it's only space. And so these are the realms of atomic interactions. Atoms are basically formed from that progression, the source, the progression of the natural reference system. It has to be reversed, and then it has to be rotated in 3 dimensions, and that becomes an atom. So an atom is really a 3-number set to a combination of rotations, 2 two-dimensional rotations that alternate, and 1 optional 1-dimensional rotation. And so Larson's periodic table includes those 3 numbers. And those are the numbers that he basically uses to derive his equations for things like the specific heat patterns. Okay, now I'm just going to read from this and see if I can try to get to the end of the chapter. He does get to some very interesting stuff at the end, but for a few minutes here, it's a little bit prosaic. So the tendency of the atoms, and now we're looking at specific heat patterns. Remember, the specific heat is like how much heat do you have to put into something to raise it by a certain temperature, raise something by a certain temperature. So it's basically the rate of heat effectiveness. The tendency of the atoms of multi-atom molecules to form thermal groups is particularly evident where the molecules contain radicals, because of the major differences in the cohesive forces that are responsible for the existence of the radicals. The extent to which the association into thermal groups is maintained naturally depends on the relative strength of the cohesive and disruptive forces. Those radicals such as OH and CN, in which the bonds are very strong, act as single thermal groups under all ordinary conditions. Those with somewhat weaker bonding, CO3, SO4, and NO3, also act as single units at the lower temperatures. Thus, we find that at the initial points of both the first and second segments of the specific heat curves, there are 2 groups in MnCO3, 3 groups in Na2CO3, and 4 groups in KAl, the quantity SO4, 5 in Ca3, the quantity PO4, and so on. At higher temperatures, however, radicals of this class split up into 2 or more thermal groups. Still weaker radicals, such as ClO4, constitute 2 thermal groups even at low temperatures. It was mentioned in Volume 1 that the boundary line between radicals and groups of independent atoms is rather indefinite. In general, the margin of bond strength required for a structural radical is relatively large, and we find many groups commonly recognized as radicals crystallizing in structures such as CaTLO3, the CaTLO3 cube, in which the radical as such plays no part. The margin required in thermal motion is much smaller, particularly at the lower temperatures, and there are many atomic groups that act thermally in the same manner as the recognized radicals. In Li3CO3, for example, the 2 lithium atoms act as a single thermal group, and the specific heat curve of this compound is similar to that of MgCO3 rather than of Na2CO3. Extension of the thermal motion by breaking some of the stronger bonds at the higher temperatures gives rise to a variety of modifications of the specific heat curves. For example, MOS2 has only 2 thermal groups in the lower range, but the S2 combination breaks up as the temperature rises, and all atoms begin vibrating independently. VCl2 similarly goes from 1 group to 3. Splitting of the radical accounts for a change from 2 groups to 3 in SrCO3, from 1 group to 3 in AgNO3, and from 2 to 6 in the quantity NH4 to SO4. All of these alterations take place at or prior to the first transitional point. Other compounds make the first transition on the initial basis and break up into more thermal groups later. In a common pattern, a radical that acts as one thermal group at low temperatures splits into two groups in the temperature range of the second segment of the curve, just as the CO3 radical in SrCO3, PbCO3, and similar compounds does at a lower level. There are a number of structures such as KMNO4 and KiO3 where this increases the number of groups in the molecule from 2 to 3. Pb3, the quantity PO4 in which there are two radicals, goes from 5 to 7, and so on. The effect of water crystallization is variable depending on the strength of the cohesion. For example, BaCl2 H2O acts as 3 thermal groups at the lower temperatures, the water molecules being firmly bound to the atoms of the compound. As the temperature increases, these bonds give way, and the molecule begins vibrating on a 5-group basis. In Al2, the quantity SO4 6H2O, .6H2O, and in NH4 Al, the quantity SO4 .12H2O. The bonds with the water molecules remain fixed through the entire experimental range up to about 300 degrees Kelvin. And the thermal groups in these hydrates are 5 and 6 respectively, just as in the corresponding anhydrous compounds. An example of a drastic change in thermal behavior due to the disruption of interatomic bonds by thermal forces is shown in Figure 12. The radical CrO3 in the compound AgCrO3 is a single thermal group at very low temperatures. There is a general separation into two groups in the temperature range up to the first transition point, and the change to the 2-unit vibration is made on the basis of a 2-group radical. At about 150 degrees Kelvin, all 4 atoms in the radical begin vibrating independently, and the molecule undergoes a transition from the second segment of a 3-group curve to the second segment of a 5-group curve. At about 250 K, the compound makes the normal transition to 3-unit vibration, continuing as 5 thermal groups. The compounds used as examples in the foregoing discussion were selected mainly on the basis of the availability of the experimental data within the significant temperature ranges. For an accurate definition of the slope of each of the straight line segments of any empirical curve, it is necessary to have measurements in the temperature range where the deviations due to the proximity of the transition point are negligible. The examples have been taken from among those of the experimental results that satisfy this requirement. In a theoretical treatment of specific heat such as that in this present work, it is necessary to deal with this quantity on a per molecule basis. For practical application, however, it is more convenient to use the specific heat per unit of mass, and most of the collected data are expressed in this manner. It should be noted that the effect of association into thermal groups is to reduce the specific heat per unit of mass. For this reason, the specific heat of most complex compounds is relatively low at low temperatures and rises toward the values applicable to individual atoms as increasing temperature breaks up the original thermal groups. The simplest organic compounds, those composed of only 2 or 3 structural units, generally divide into no more than 2 thermal groups. Many of the somewhat larger organic molecules, particularly among the ring structures and branched compounds, follow the same rule. The specific heat relations of these compounds are similar to those of the inorganic compounds, except that there are more organic compounds in which the thermal motion is restricted to one rotational unit. These substances, the hydrocarbons and some other compounds of lower elements, undergo a transition to a positive initial level on reaching their first and only transition point. The resulting specific heat curve, the one illustrated in Figure 3, is not much more than a straight line with a bend in it. A few compounds, including ethane and carbon monoxide, even omit the bend and do not make the transition to the positive initial level. Further addition of structural units such as the CH2 groups to the simple organic compounds results in the activation of internal thermal groups, units that vibrate thermally within the molecules. The general nature of the thermal motion of these internal groups is identical with that of the thermal motion of the molecule as a whole. But the internal motion is independent of the molecular thermal motion, and its scalar direction, inward or outward, is independent of the scalar direction of the molecular motion. Outward internal motion is thus coincident with outward molecular motion during only 1/4 of the vibrational cycle. Since the effective magnitude of the thermal motion, which determines the specific heat, is the scalar sum of the internal and molecular components, each unit of internal motion adds 1/2 unit of specific heat during half of the molecular cycle. It has no thermal effect during the other half of this cycle when the molecule as a whole is moving inward. Because of the great diversity of the organic compounds, the specific heat patterns occur in a variety that is correspondingly large. The effect of internal motion in those of the organic compounds in which it is present is well illustrated, however, by the specific heats of the normal paraffins. The values of the initial levels and the specific heat at T1 for the compounds of this series in the range from propane to hexadecane are listed in Table 21, together with the number of internal thermal units in the molecule of each compound. Then he's got a table of all of these organic compounds here that are in that series: propane, butane, pentane, heptane, octane, and so on, and looks at the specific heat there. Propane and butane have only 2 molecular thermal groups corresponding to the positive and negative ends of the molecules, and their specific heat at T1 is the normal 2-group value, 9.27. Beginning with 2 internal groups in pentane, each added CH2 structural group becomes an internal thermal unit. Adds 2.317 to the total specific heat of the molecule at the transition point. The initial level of the first segment of the specific heat curve is minus 2.64, the 2-group value in the lower compounds, and changes slowly, adding units of negative 1.32 as the length of the chain increases. The initial level of the second segment is 2.64 in butane and propane. In the higher compounds, each of which consists of N structural groups, CH2 and CH3, this second initial level is 1.324 N. The values thus derived theoretically are all consistent with the experimental curves. In a few cases, the intersection of the 2 curve segments may not coincide with the calculated specific heat of the transition point. But these deviations, if they are real, are small enough to be explainable on the basis of changes in the temperature factors, the nature of which will be one of the subjects of Chapter 7. Branching of a hydrocarbon chain tightens the structure and tends to reduce the number of internal thermal units. For example, octane has 5 internal thermal units and a specific heat of 20.86 at the transition point, but the 2,2,4-trimethylpentane, a branched compound with the same composition, has no internal motion at all, and the T1 specific heat of this compound is 9.27, identical with that of the C3 paraffin propane. Ring formation has a similar effect. Ethylbenzene and the xylenes, which are also C8 compounds, have some internal motion, but their T1 specific heats are 11.59 for 1 internal unit and 13.90 for 2 internal units, respectively, being well below the octane level. In figure 13, the specific heat curves of hexane, straight chain, and benzene ring, both C6 hydrocarbons, are contrasted. The subject matter of this and the preceding 5 chapters consists of various aspects of the volumetric and thermal relations of material substances. The study of these relations was the principal avenue of approach to the clarification of basic physical processes that ultimately led to the identification of the physical universe as a universe of motion, and the determination of the nature of the fundamental features of that universe. Their relations were examined in great detail over a period of many years, during which thousands of experimental results were analyzed and studied. Interpretation of the accumulated mass of information into the theoretical structure was the first task undertaken. After the formulation of the postulates of the reciprocal system of theory, and it has therefore been possible to present a reasonably complete description of each of the phenomena thus far discussed, including what we may call the small-scale effects. And unfortunately, there's one more paragraph that I'm not going to get through. So I will go back probably a paragraph tomorrow and finish up this chapter. He's dragging on and on with the details here. But this important stuff at the end of the chapter, we will talk about tomorrow. And then I think after that, we're going to get into the next chapter, specific heat patterns or temperature relations, which is great.